2. The chemical reaction proceeds as the reagent travels through the PFR. In this type of reactor, the changing reaction rate creates a gradient with respect to distance traversed. At the inlet to the PFR, the rate is very high, but as the concentration of the reagent decreases and the concentration of the product increases, the reaction rate slows. Some important aspect of the PFR is all calculations performed with PFR assume no upstream or downstream mixing as implied by the term of plug flow. Reagent may be introduced into the PFR at location in the reactor other than inlet. In this way, a high efficiency may be obtained, or the size and cost of the PFR may be reduced. A PFR typically has a higher efficiency than a CSTR of the same volume. That is, given the same space-time for resident time, a reaction will typically proceed to a higher percentage completion in a PFR than in a CSTR. This is not always true for reversible reactions. For most chemical reactions of industrial interest, it is impossible for the reaction to proceed to 100% completion. The rate of reaction decreases as the reagents are consumed until the point where the system reaches dynamic equilibrium. The equilibrium point for most systems is less than 100% complete. For this reason, a special process such as distillation often follows a chemical reactor in order to separate any remaining reagents or byproduct from the desired product. And now we will go straight to the video that shows the real process in the real PFR reactor. Hope you guys enjoy!
Description for each generation. In first generation, reactors were developed in 1950 to 60s and very few are still running today. They have been referred to as early prototypic reactors. In second generation, in mid-1960s, active safety system was often used in this generation's reactors. It involves electrical or mechanical operation on command, which means activated by human controllers and cannot operate if electrical power systems are shut down. About 90% of nuclear power plants operating today employ second generation technology. Many of them have incorporated some passive or inherent safety features, requiring no active control operational intervention for accidents or avoidance in the event of malfunction, and rely on gravity, natural convection, or resistance to high temperatures. Third generation, in mid-1990s, the advanced reactors were developed. The design incorporates further passive safety systems. It to increase reactor safety operating without human intervention or electrical power. In the fourth generation, the design of this type of reactor are still on the drawing board. It not be operational before 2020 at the earliest and probably later. The time taken for its radioactivity to fall to a safe level will be far shorter. Many designs will be fast neutron reactors. It tends to have closed fuel cycles and burn the long-lived actinides, now forming part of spent fuel, so that fission products are the only high-level waste. This picture is the diagram and description of the advanced reactor technology.
Nowadays, PFR reactor is being widely used in the heavy industry. In this chapter, we will discuss on the PFT, PNID, and the schematic diagram on the production of benzene that using the PFR reactor. So what will happen next? Let's check it out.
The stream introduced into the reactor R1. This reactor is vertical vessel packed with catalyst. Main part of the process happen is in this reactor where the main reaction which produces benzene happens. The reaction occurs when the reactant which is toluene react with hydrogen, produce benzene and methane as a product. This is a catalytic exothermic reaction where the temperature is controlled by injecting hydrogen into the reactor. The hydrogen is injected at 40.4 kmol per hour, 44.96 degrees Celsius, and 25.5 bar. The exiting stream exits at 24.81 bar and 671 degrees Celsius. It contains methane, benzene, toluene, and hydrogen. The one-pass conversion is typically around 75%. The process then continues to the separator feed preparation phase, where it begins with introducing the stream into a cooling water heat exchanger E2. This heat exchanger cools the product stream to 38 degrees Celsius, which condenses most of the toluene and benzene in the stream.
Okay.
In conclusion, the PFR reactor undergo a modification and evolution to increase the efficiency of the reactor itself. The latest technology allow to achieve the optimal reaction and lead to the increasing of the production profit. This is due to the more economic and safe energy reactor.